All right. 6.4, we got to the part where we're talking about functions and logarithms. So we're going to talk about domain and range of a logarithmic function. So functions, it'll come up in this section. Functions with logarithms. So f of x is equal to log base. It really doesn't matter. We're going to use a here just to get a generic idea of what's going on of x. Okay. A logarithmic function has a domain from 0 to infinity. Or a better way to say this is that you can only take the log of a positive number. Can't take the log of a negative number at all. Okay, so or 0. We can't take the log of 0. So anything we're taking the log of, it needs to be a positive number. So it's really x is greater than 0 or from 0 to infinity. Okay. All x is such that x is greater than, not equal to, but greater than 0. No equal to on that. Okay, so domain from 0 to positive infinity for logarithmic functions. Just a basic one. We'll get to some that change a little bit according to what is inside of that log. We'll see that in just a second. Typically, the range would be from negative infinity to positive infinity as just a rule of thumb. Not always going to be that, but it happens that way a lot. Logarithms and exponentials are tied together, that the domain of a log is the range of an exponential. Reason being is that the logarithm is the inverse of an exponential. And the exponential is an inverse of a log. Okay. So that kind of just gets us there. All right. So let's look at some examples and find the domain and of these logs. Range negative infinity to positive infinity. There's not much changes of that in the college algebra. You really don't get into anything that does much other than changing the domain. Log base 2 of x plus 3. All right. So if we're going to state the domain, what kind of numbers can we take the log of? Positive only. So we need to know when is x plus 3 positive. So we just take whatever we're taking the log of, the part of the function, x plus 3, and we just set it greater than 0 and solve it. If we solve that, that's going to get us only the x's that are giving us a positive value inside of the log. So subtract 3. X has got to be greater than negative 3 to be valid in this function as part of the domain. So our domain would be all x's such that x is greater than negative 3. There's our set notation. Interval notation would be negative 3 to infinity. Parentheses on each end there. Domain. Really, really easy idea. Log base 5 of 1 plus x over 1 minus x. A rational expression inside of a logarithmic function. So if we're going to take the domain of that, we need to know when is that fraction greater than 0. So 1 plus x over 1 minus x. When is that greater than 0? Okay, so you got to think about rational functions or rational expressions and rational inequalities. When we're dealing with rational inequalities, we're dealing with fractions. What part of a fraction could be negative and get us a negative value for that fraction? If the numerator's negative, then we got an issue of it being a negative fraction. Or if the denominator's negative, we got an issue of it being a negative fraction. If both of them are negative, then it turns back to positive, so it's okay. So we need to know, when is this fraction greater than 0? And the way you want to do that is you find those key places where what's in between positive and negative. 0. So when is the numerator equal to 0? Yeah. And when is the denominator equal to 0? At positive 1. So those are the key places that we can't have. If the numerator was equal to 0, it really doesn't matter what the denominator is, right? Because the fraction turns into 0, which we know it cannot be. If the denominator is 0, we got a major issue because you can't even divide by 0. So that's where that happens at. So we want to test some values at those places, at -1 and +1, or not at those places, but around those places. So we got two places we're setting up an interval test here. Open circles on those because they're not included. We know x cannot be -1 because that would give us 0, and we're looking for things that are greater than 0. So we want to test some values on the number line that are to the left of -1 just to see what it does to the fraction. So if I pick a number to test over here, so I pick -2 and plug that into the problem. 1 plus -2 over 1 minus -2. What does that give us? That gives us -1 over +3, which is a negative fraction. Is -1/3 greater than 0? No. So with this area to the left of -1 is false. So we know that's not going to be part of our domain. I'm going to pick a number that's between -1 and +1. 0 is a good one. You could pick any of those fractions that are there if you wanted to. I don't know why you would, but you could. 0 is the easiest one to plug in. So if I plug in 0, 1 plus 0 over 1 minus 0. That's 1, right? Is 1 greater than 0? This area is true. It's possible that this is the only true area of our intervals. But it's also possible that this area might be true as well. So we need to test something in that area as well. So I'm picking for a number that's bigger than 1. I'll pick +2. Plug that in. 1 plus 2 over 1 minus 2. That'd be 3 over -1, which is -3. Is -3 greater than 0? No, so it's false. So the domain, because of that interval from -1 to +1 being the only true area, the domain is all x's such that x is between -1 and +1. There's our set notation for that. Interval notation would be -1 to +1. Okay. The domain of that particular one. The rational ones, you've got to set up that interval. And the interval numbers that you want to test around are coming from setting the numerator equal to 0 and the denominator equal to 0. Get those. That's where you're going to get those from. So it's just solving rational inequalities is what that's from. Another exceptional one would be maybe we had an absolute value we were taking the log of f of x log base 3 of the absolute value of x. Really nothing else in there with that. So when we're looking at absolute value, we're setting up an inequality. That absolute value, when is it greater than 0? Okay, so when is that going to be? when x isn't equal to 0, right? The only thing x can't be for that to be true is x cannot equal 0. That's the only thing that doesn't work in that setup. So our domain, pretty easy on this one. All x's such that x does not equal 0. Interval notation would be negative infinity up to 0, union 0 to infinity. Pretty easy there with the absolute value when it's just plain x in there. Kind of complicates a little bit when you've got maybe f of x equal to log base 9 of the absolute value of x plus 2. So a little bit more inside of that absolute value here instead of just plain x. Makes it a little bit more interesting. The idea still, though, when is that absolute value of x plus 2 greater than 0? When does what occurs there? Yeah, what makes x plus 2 equal 0? Well, it's negative 2. X can't be negative 2. A pretty easy solve there. Okay, so our domain, all x's such that x does not equal negative 2. So that would be negative infinity up to negative 2, union negative 2 to infinity. Good job. Really easy thing here. Finding domains of logarithmic functions.
Now that would just be any number that's if we had something like that would be any number now that's higher, that's above 0, right?
This just says any number that's not negative 2.
No, I'm talking about in your absolute value. Like we
That's what I'm saying. That inside of that, any number that's not negative 2 works.
I'm talking about if we had a different number or anything in there. It can't be the negative version of that number.
Whatever is in here has to be a positive number. That's what the log. You can't take the log of a negative number. That's like undefined. Is what the log of a negative number is. You cannot take the log of it. So whatever's inside of that logarithm has to be positive. Now is that what you're after there? Yeah. All right.
I'm just thinking if we have bigger numbers on a test.
It won't. They don't get any more complicated than that idea right there. That it's got to be a positive number. All right. So let's look at solving. Solving a logarithmic equation. Last part of 6.4. My favorite part of 6.4. What letter around here? E. We have log base 3 of 4x minus 7 equals 2. All right. A couple different ways to do this. One way is to think about this logarithm as an exponential and rewrite the problem as an exponential. And what makes that a good idea here is that you only have a log on one side. You don't have logs on both sides. You just got it on one side. And you could rewrite that as an exponential by thinking, okay, well, if it's log base 3, how do I turn that into an exponential? Well, the base becomes 3. The exponent, that's what the log is equal to. So it's 3 squared equals 4x minus 7. And then that's a pretty easy equation to solve because we know what 3 squared is, right? Turns into 9. And now we just have 9 equals 4x minus 7. And solve that just like algebra 1. Plus 7. Maybe 7th grade math. 4x divided by 4. X equals 4. That's a very valid way to do that. We'll see some other ways in just a minute that work as well to do that. Okay. So thinking about a logarithm as an exponential, always helpful. Okay. All right. Here's another one that could be helpful to think about in that way. Log base x of 64 is equal to 2. We want to think about that as a exponential. Is it just 8? Because if we rewrite that as an exponential equation, it's x squared equals 64. The base of the log, what it's equal to is the exponent, so that's x squared, and then what you're taking the log of is 64. If I solve that, take the square root, it's not just 8. It could be negative 8. Because negative 8 times negative 8 is what? 64. Still just like positive 8. Okay? That's the base, not what we're taking the log of. Remember, the rules are that whatever you're taking the log of has to be a positive number. What we're taking the log of here is positive 64. The base, there's not a rule for that. The base can be anything. But what you're taking the log of has to be a positive number. And it is 64. That base could be negative 8. It's okay for that to happen. So we do have two answers on this one. It's negative or positive 8 for that. It's handy. Such case occurs. All right, let's do log base 3 of 3 to the 6x equals 42. Here's one of those log properties showing up that really makes things a lot easier. Anytime the base matches that number, they cancel each other out. That 6x equals 42. That makes it so much easier, right? That problem is easy to solve. Divide by 6. X equals 7. The only thing we need to check to make sure of is if I plug a 7 into the problem, am I taking the log of a positive number? So 3 to the 42nd power, is that a positive number? Yeah, it is. So that makes that valid. You got to check those answers to make sure that they work. If they don't, then you throw them out. Okay. Let's look at an exponential equation. 27. Let's do 27. 81 to the x is equal to 27. All right. So this type of problem can be solved a couple of different ways. One way would be to try to turn it into an exponential equation on both sides, where you have 81 and 27. What's the relationship between 81 and 27? Both divisible by 9, which means they're both also divisible by what? 3. So 81 can be turned into 9 squared, but 27 is 9 times 3. It's not 9 to a power. So that's why I bring up the 3. 81 is 3 to what power? To the 4th, and 27 is 3 to the 3rd. So we have 3 to the 4th to the x equals 3 to the 3rd. Okay? Well, that gets us 3 to the 4x equals 3 to the 3rd. As an exponential equation, since the bases are the same, what's my equation end up being? 4x is equal to 3. Now, what's the math that makes that happen? Yes, that's the equation we're going to solve. But what's the math that makes that happen? The math that makes that happen is directly related to this problem on G. That I could use a log base 3 to cancel out those bases of 3. That's really the math that makes it work out. That if I do log base 3 of 3 to the 4x equals log base 3 of 3 to the 3rd, the log base 3's cancel out those bases of 3. And then we have 4x equals 3. That's the math that makes that happen. Okay? That's important to know because you're not always going to be able to turn that number over there on the right into 3 to a power. If that would have just been 25 there instead of 27, then you can't do the exponential stuff. You've got to think of logs. Okay, so here we just divide by 4. The x is 3/4. And that works in that problem. It gives us the right answer. We didn't have a log in the original, so we don't have to worry about it turning negative on us. Where that comes into play as an important part would be 3 to the 5x is equal to 24. Here's a problem where that using a log to solve is very important.
What did you end up on? the end of it.
4 over 3, or 3 over 4, excuse me. Now, with this one, we've got 3 to the 5x is equal to 24. For simplicity, we would love it if 24 would turn into 3 to the power, but we know it doesn't because 24 is 12 times 2, and 12 is 4 times 3. So there's a number other than a 3 in there that messes things up. So we can't do that with this. So what we want to do is cancel out that base. What log base will cancel out a 3 as a base? Log base what? Log base 3. So if we do log base 3 of each side, that side they cancel out. Give us 5x. On the other side, I've just got log base 3 of 24. Log base 3 of 24 is a number. It's a big, long decimal number. Not a big number. It's a decimal number, not a big number. But it's a decimal number. It's got a lot of digits. Okay? How do I get x by itself? Yeah, divide by 5. And then I get x equals log base 3 of 24 divided by 5. That's the exact solution, is that. We want to get a decimal approximation for that as well. So with the graphing calculator, it'll do the log base stuff for us. We'll use the right command. You can hit math. This is how I always do it, is math, and then press the up arrow till I get log base, and then type in log base 3 of 24. Get that answer, and I'm dividing that by 5. 0.5. We'll go 4 decimal places here. 0.5786. If you don't have a graphing calculator, or for whatever reason your graphing calculator died, or you couldn't remember how to get log base 3 of 24 in there, you can do log of 24 with the log button over here on the left, right here. If I do log of 24, close parentheses, divided by log of 3, that gets us the same result. Notice these two decimals are the same. This is the change of base formula is what that's called. Yes, ma'am.
I was just wondering, whenever we get a log base, do we get that because we're finding something that will help cancel out?
Yes, ma'am. That's right. Right. On the problem here, we had on this side, erase this stuff. We had a base with the exponent, with the variable and the exponent. We could not turn 24 into that same base. So that's where the log base 3, when we put that in there, that's to get rid of this base of 3 and get that exponent down, the variable down to where we can just divide or add or subtract or whatever we needed to do out of that. All right. Good question. Good job. All right. Let's do another. What letter are we on here? J. 2 to the 3x plus 1 is equal to 15. So here we have a little more complex exponent. Is there any way to turn a 15 into 2 to a power? Yeah, because on the left side I got a base of a 2. So I'm thinking, if this was 16, I'm in business. But it's 15, so I can't do that. So what do I do to get rid of that base of a 2? Perfect. If I take log base 2 of both sides, that'll cancel out right there. That's what taking the log base does, is it cancels out. Y'all got a Casio. Good luck. Good luck. I haven't worked with those enough to be able to just spit out where it's at. It's in there. I know it'll do it. I'm just not sure where. You find it? Yeah. Good. All right. So the log base 2 canceled out the base of a 2. On the other side, we got log base 2 of 15. That's just a number. It's like 6. It's not 6, but it's a number. Okay. It's just like the number 6. Okay. Now, we just need to get x by itself. How do I get x by itself? Not yet. Got to get rid of the 1 first. So I'm going to subtract 1. So there's 3x is equal to log base 2 of 15 and then a minus 1. And I kind of put some space there so we know, hey, log base 15 is the number and we're subtracting 1 from it. Okay? And then the last step is divide everybody by 3. So we know x is equal to log base 2 of 15 minus 1 over 3. Let's get a decimal approximation for that. Math. Going to log base 2 of 15. Subtracting 1. Getting that answer, and I'm dividing it by 3. 0.9690. You round to 4 decimal places. This 6 makes the 9 go up. If the 9 goes up, the 8 has to go up. 0.9690. Right. Easy enough. No, because we had 0.9689 and then it was a 6 after that. We look at this 6 right here. That 6 right there makes this 9 go up. It becomes a 10. So you got to carry 1 digit over here to the 8. And 8 doesn't make 10. It goes to 9, not 10. So the 6 stays the same. And it's one of those weird ones where if you round the 9 and it has to go up, then the next digit has to go up, but nobody else does. Good question, because that's always something that kind of trips some folks up, and they will always put the answer choice where if you rounded all of them up an extra one, that seems to be the case. All right. Oops. Last thing, it's all in the same family as solving, is the inverse. If we have a logarithmic function, we'll use natural log because that's logarithmic. It doesn't really matter what the base is as far as whether it has an inverse or not. If we're going to find the inverse of that, I don't know what letter I'm on here. Okay. Find the inverse of that. To find the inverse, what's an inverse function do? Swaps an x and y. Flips the x, the domain and the range swap. So x and y swap. So in our case, we're going to have x over here and natural log of y minus 3 here. Then we have to solve it for what? Y. We got to get y by itself again, right? So how do we undo a natural log?
Natural exponential.
The exponential is the inverse of a natural log, because the natural log is log base e. So we exponentiate with an e on each side. Whatever the base of your log is, we're going to use that as the base on both sides. And on this side, e to the x just turns into e to the x. The natural log and the e as the base, they cancel one another out. Just like the log base 3 cancels out a 3 as the base, they cancel each other out. And there we have y minus 3. Now there's no more natural log in there. So we get y by itself again by doing what? Just add 3. E to the x plus 3 is equal to y. So our function inverse is equal to e to the x plus 3. Let's do one with a different log in there. F of x is equal to log base 4 of x plus 5. Okay. If we're going to find the inverse, what's an inverse do again? Swaps your domain and range. So this is x equals log base 4 of y plus 5. We just swap x and y first. Now, what do we exponentiate with to get rid of the log base 4? 4. Whatever the base of your log is, that's what you're going to use. So 4 becomes the base. So that's just a little caret symbol saying that's the base now. Base of a 4 cancels out the log base 4. That's 4 to the x is equal to y plus 5. How do you get y by itself? Yeah. So 4 to the x minus 5 is equal to y. So we rewrite that function inverse is 4 to the x. We remember some things about inverses. If you were to graph this inverse function and this logarithmic function at the beginning, if you graph those, what line do they reflect across? Anybody remember? Not the y-axis. Not the x-axis. We're not in 3D. We're in 2D.
The origin?
It's actually the y equals x line, which goes through the origin. They reflect across the y equals x line. So there's a checking place that you can do. Graph them. They should reflect across the y equals x line. So that diagonal, it goes through there. If you wanted to see that.
So how do you solve for a variable in the denominator?
You multiply.
Okay.
To get, because the denominator is division, so you would multiply to get it up to out of the denominator. That would be what I would do. All right, that's section 6.4. So we're finished with what we should have finished last week. So let's get to this week's stuff. Section 6.5 is where we'll start. Properties of logarithms. Properties of logs, we've already used some of them. I'm just going to list them here. We'll list some of them. This number 2 we've already used. We use that today to solve. That's one of those properties. We've used this one. That's one we just talked about using to find the inverse. So those are ones we're kind of familiar with. The first property, if we think exponentially, base of a to the 0 power, anything with the 0 exponent equals what? 1. So that's why that property's there. Those really, we don't use a ton when we're talking about properties of logarithms, but they're there, so we kind of need to know them. Let's get into the ones you actually do use a lot, and that would be log base a of a to the r. Again, the log bases cancel out. We just get the variable that's in the exponent back. If we're multiplying inside of a log, that turns into addition. And if multiplication turns into addition, division turns into subtraction. Top minus bottom. Here we have log base a of something to a power, an exponent. That r is an exponent there. The property allows us to pull that r down to the front and make it r times log base a of m. Instead of having an exponent, we can pull that down to the front and make it a multiplication problem, which is easier to undo. That's kind of the idea here. These properties allow us to undo things a little easier. These last two you don't use very much, but I've got to show them to you just because Mr. SQ says I do. a to the x is equal to e to the x natural log of a. That if you did all the math here and put this x back up here, you get e to the natural log of a to the x, and the e and the natural log cancel each other out. You get a to the x equals a to the x. It's really a useless property. You won't use it. The natural log of e is equal to 1. That's just like log base a of a.
What's that?
A is just a variable.
Okay, thank you.
It's just a variable. E is the exponential number. E and x is a variable. A is just some arbitrary other variable or number. It doesn't matter. Okay. All right. So what we're going to do here is we're going to take some logarithms and we're going to expand first, get them separated by using these properties, and then we're going to condense or write them as a single logarithm. Okay, that's our job for today or for this section. Okay, so let's expand. The instructions you might also see would be write as a sum or difference. Okay, those mean the same thing. I'll say expand because that's what you're doing. You're taking a single log and breaking it apart. Okay, so we're going to take example A, log base A of x square root of x squared plus 1. All right, so what's going on the inside of this log? We got an x. What's going on between that x and the square root stuff? Are they adding, subtracting, multiplying, or dividing? They're multiplying this x times this square root stuff. So the multiplication turns into what with logarithms? Addition. So we would be able to take that as log base A, and it doesn't matter what base it is. I'm using log base A. It could be log base 2. It could be log base Easter eggs. It really doesn't matter what the log base is there. The rules are still the same. So I have the x, and then I have log base A of the square root of x squared plus 1. Now this is where they get a little sneaky, and they kind of try to disguise it and think you think you're done. I split it apart. I got it written as a sum. I'm done. No, you're not. Because it's got the square root in there. Got to get rid of it. Square root is what exponent? 1/2. This is the same thing as x squared plus 1 to the 1/2 power. And we have that property up here that lets us bring that exponent out to the front. So we would rewrite this problem as log base A of x plus 1/2 log base A of x squared plus 1. That would be complete. Because we don't have a log property that breaks apart addition. We have a log property that breaks apart multiplication, breaks apart division, but we don't have one that breaks apart addition. Okay. So that exponent, they kind of try to sneak that in on us. We got to keep an eye out for it. Okay. Any kind of root, it'll always come out as an exponent. Yeah. If it's a cube root, it's going to be 1/3. If it's a fourth root, 1/4. That sort of idea. Anytime you see that, you're going to have to pull it apart there. Let's look at another one. Natural log. We'll use that. X squared over x minus 1 cubed. What's the big thing going on here? Fraction. So that's what operation? It's division, which turns into subtraction. So we're going to end up with natural log of x squared minus natural log of x minus 1 cubed. But we could also do what? What about these guys? Yeah, drop them to the front of each term. So that's 2 natural log of x minus 3 natural log of x minus 1. And that's expanded as far as is possible. If you can do that in one step and not, you don't have to write 2 or 3 steps here. Some of you can do these in your head quickly and get those done. If you've had some experience with this, you probably are bored right now. So, and you may be bored right now even if you don't have experience with this. That's okay. I don't. Let's get a little robust one here. There's a lot going on. Got a couple of things in the denominator. Quite a bit going on in the numerator there. So, what's the biggest part of this problem? Fraction. The division with all of that stuff. The big thing is it's dividing. So, that means I'm going to end up splitting it into a subtraction problem where I have, what can I make this into? Good job. Now, this denominator here's got 2 different things in it. So how many things am I subtracting? 2 different things, right? I'm subtracting log base 5 of x cubed and log base 5 of x plus 1 to the 4th. Right? What can I do to each one of those? Bring the exponents to the front. That's the one you want to recognize. The easiest one is that exponent to the front idea. Because they're both in the denominator, it's going to be a minus 3 log base 5 of x minus 4 log base 5 of x plus 1. Okay. Both of those become minus because they were both in the denominator. That makes sense. They would both be subtracted because they were both in the denominator. The 3 came from the x cubed. The 4 came from the 4th power on the x plus 1. That's expanded as far as you can. Remember, you don't have a rule that lets you split addition. You don't have rules that let you split multiplication, division, or exponents. Okay. All right. Let's take this same idea and go the other direction. The opposite of expanding is condensing or shrinking into one logarithm or rewriting as one log. So let's condense into a single logarithm. Again, the base doesn't matter on this. We got log base. Log base A of 7 plus 4 log base A of x. The only thing that has to be the same is the base on the logs to combine them back together. If the bases are different, then you can't combine them back. They don't do that to you in college algebra. They're going to give you everything. Either a couple of pieces have the same log base and a couple other pieces have a different log base. That's the most complex they'll give you. Most of the ones you're going to see in Math 140, they all have the same log base. So here, both of them are log base A. So we just need to condense this back together. So it's an addition problem, so we know it came from what? Came from multiplication. So is there anything we can do to this piece?
We can go ahead and do log base A.
Yeah, it's going to be log base A of 7 times something. What's that something? Not 4x. X to the 4th power. That's the right thing. Because this 4 that's in front came from up there. We put it back to the exponent. Anything that's in front of a log was an exponent. So you put it back up there. Okay, so we have log base A of 7 times x to the 4th power. And that's it. You condense it into one log. Nothing else to do there. 2/3 natural log of x minus natural log of x squared minus 1. We have a subtraction problem, so we know it's turning back into what? Division problem. So we're going to have natural log of some stuff divided. What's the numerator? X to the 2/3 power? 2/3, yeah. Sorry, my handwriting's not great. And then on the denominator, we're going to have that whole thing there, x squared minus 1, right? Now, this is one way to write it. Technically, that's correct. But what's another way to write x to the 2/3? Cube root of x squared over x squared minus 1. Both of these are correct. Understand that they may or may not go this far. It's possible though. Whatever the denominator is in your fractional exponent, that's the root that you're taking. The numerator is the exponent on what's left inside. Very simple to turn into that. They don't always turn it into that. They just, this particular textbook is a little wish-washy about, sometimes it does and sometimes it doesn't, depending on the complexity of the problem that's going on there. So I like to show both ways, because who knows what you're going to take next. You're going to take calculus. They may or may not change it there, depending on if you're taking a derivative or not, or something fun like that. Calculus is fun. I like calculus. But if you stink at algebra, calculus is not your friend. All right, so all log base 5s. Everybody's a log base 5. So we got log base 5 of x plus log base 5 of 9 plus log base 5 of x squared plus 1 minus a log base 5 of x minus 3. What all is going on here? Confusion. There's a lot of stuff. There's going to be what? Some of the multiplication, some are dividing, right? Which ones are multiplying together? All the pluses, right? So the x, the 9, and the x squared plus 1, they're all multiplying together. Where would they be in the division problem? They'd be in the numerator because they're in front, right? So it's really not that complex here. It looks like it is, but we can combine that into being 9x, x squared plus 1 over what? X minus 3. We're done. So it's really not that complex. It looks like it's just murders, but it's not. Anything that's positive or has a plus sign in front of it is going to be multiplying. Anything that has a minus sign in front of it is going to be dividing. Subtraction is dividing. Okay? That's what you got to keep in mind. Uno más. 3 log base 10 of x plus 2 log x plus 5 minus log 12 minus 3 log x minus 2. Pretty long one here. All the same log base though. All log base 10s. No right 10s in log base 10. Yeah. That's what's considered a common log, because all of our normal number system is base 10, so they don't write the 10. It's a log base 10. Not that it really matters when you're condensing or expanding. That would only really matter if you're solving equations. We'll get there in a minute. All right. So, what's going on here? What do we got happening? All right, we got log base 10, and what's happening at this first piece?
We got a division.
There's a division because there's some subtraction. There's some multiplication because there's addition, right?
Mm-hmm.
So what goes in the numerator of our division problem then? The multiplication stuff, right? So we got log of x cubed times x plus 5 squared. Now see where I'm getting at? The exponents go up. Okay. That sound. If you don't use that sound, it doesn't work. Okay. Then everybody else has a minus sign, so that means everybody else is where? Bottom in the denominator. Okay. What's going on between them when they're in their denominator? They're multiplying together. So it's 12 times what? X minus 2 to the third. Good job. That goes up. Fairly complex one to get out of that. The expansion is not necessarily something we use a ton to solve. The condensing is. But the expanding really helps you learn the properties. So doing some practice with the expanding of a single log into addition and subtraction can really help you get ready to do the condensing, which is what you'll actually use to solve, which is the next section. 6.6, solving. Logarithmic. And exponential equations. Instructions are to solve. 2 log base 5 of x equals log base 5 of 9. All right. So obviously this is a logarithmic equation because it has logs in it. So we've got to think about, okay, if it's log base 5 on this side and log base 5 on the other side, whatever we're taking the logs of should be equal, right? The only difference here is that on this side we got a 2 in the front, and then on this side we don't have anything. How can I get that 2 not in the front? Make it back to the x squared, right? So using that log property, we can condense that to be log base 5 of x squared is equal to log base 5 of 9. Now, the log bases are the same. What to do to get rid of the log base 5, what mathematically do we have to do? Cancel them out with what? As the what? It's the base, it's exponentiating. That's what you mean. It's exponentiating with the 5. That's what you're saying do. You can see it happening. So you're exponentiating with the base of a 5. That's the math that's happening. Do you have to know that when they're the same log on each side? Not really. I mean, this is what happens. They cancel out. It's just x squared equals 9. We knew that was happening anyway, right? But knowing that 5, exponentiating with a 5 is going to be helpful when we get to a tougher problem. This is a pretty easy problem. We're going to get to tougher ones. Okay? How do we solve that? Square root. Thank you. Plus or minus 3. Which one do we throw out? And why? It's not it didn't really matter what the base is.
But you can only have a positive.
That's right. In the original problem, I've got an x inside of the logarithm. If I plug in -3, I'd be taking the log of a negative number, and I can't do that, right? Remember, logs only work for positive numbers, bigger than 0, okay? So -3 gets thrown out. X equals positive 3 is the only answer that works here. Will you always throw out the negative answer? Always is a really strong word. In math, don't use the word always unless you're sure. In arguments with your significant other, don't use the word always, even if you are sure. Okay, so always is a tough word. It's really it has to be that, because depending on what's inside of that log, it could change the sign of it. We'll see some that might happen with. Okay. All right. Example B. Let's go a little more fun. Log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. There's two logs that are on the same side. Let's rub them together so we can find. Okay. Because they're on the same side and they're the same base, we think log properties. And what's going on between these two logs? They're adding, right? Adding becomes what? Multiplication. So we really have log base 5 of x plus 6 times x plus 2 is equal to 1. Now that problem looks a little smaller. Doesn't look any easier because it's got that log base 5 in it. How do I get rid of that log base 5? Exponentiate with 5 as the base. Now the log base 5 goes away. Get x plus 6 times x plus 2 is equal to 5 to the first power, which is 5. Now how do I solve that? I need to FOIL it out and multiply it together first.
I thought I might have just misunderstood or forgotten, but
Mhm.
I thought it would be 1 to the 5th power.
No, we're making whatever we're exponentiating with is becoming the base.
Okay.
So this is becoming the exponent. Or it's log base something is equal to its exponent.
Okay.
That the base is the whatever we're exponentiating with becomes the base. All right. All right. So if we multiply this out, foiling or just distributed property, whichever way you think about that, x times x is x squared plus 2x plus 6x plus 12 is equal to 5. So that's x squared plus 8x plus 12 is equal to 5. Okay, maybe that looks like something we could solve. What do we do to solve that? Because we need to get it equal to what? Why? Because it's quadratic. Technically, anything that has an exponent on x, we need to get it equal to 0 to solve. If there's another term that doesn't have the same exponent. So 8x plus 7. So here we have a quadratic. Remember we did those in chapter 4. There are a lot of ways to solve those. One of those would be factoring, or what's the other method? Quadratic formula, or you could do completing the square, which nobody ever does. I feel bad for it. Nobody uses that one. But factoring works on this one. I'm pretty decent at factoring, so that's what I'm going to use. Multiply to be 7, add to be 8, to be 7 and 1. My factors are x plus 7, x plus 1. And I solve those. Set x plus 7 equal to 0, x plus 1 equal to 0. And I end up getting two negative answers. I get a -7 and -1. I've got to check each one of them in the original problem. Go back to the original, not anything you've changed. Okay? So if I plug in -7 back in the original problem, remember the original problem was log base 5 of x plus 6 plus log base 5 of x plus 2. If I plug a -7 in for x, that'd be -1 right there. That's enough to throw it out already. Okay, so this one's gone. If I plug in -1, that's still positive 5, so that's good. -1 plus 2, positive 1, that works. It's a positive in both of them. If we checked it mathematically, log base 5 of 5 plus log base 5 of 1, that'd be 1 plus 0 is 1. So that works. So that one checked, we're going to keep it. It is possible that both of them get thrown out. That they're both what's called extraneous solutions. And you would have no solution. If all of the solutions you've got don't work, then there's no solution. That's possible that happens. Not very likely, but it does come up from time to time. Okay. Let's do one with the natural log in it. Natural log of x plus natural log x plus 4 equals natural log of x plus 6. Lots of natural logs. Don't overthink it, but don't underthink it either. Think it just the right amount, Goldilocks. The left side got two different things. So what could I do to that? Yeah, I could condense that side together and just get natural log of x times x plus 4. That gets it a little better. It's a little shorter problem now. Now the natural logs are a problem. How do I get rid of those mathematically? Exponentiate with e. That cancels them out. You get x squared plus 4x equals x plus 6. I just distributed the x here. X times x is x squared. X times 4 is 4x. This step right here, natural log is log base e. It's used enough. It's got its own special thing like pi is used enough to have 3.145, 159, a bunch of stuff after that. Natural log is log base e. So that's why we're using e to exponentiate. Okay? Now, to solve this, what do I have to do? Get it equal to 0. So subtract x, subtract 6. That's going to be x squared plus 3x minus 6 equals, not minus. I miscopied the problem. So that's a minus 4. It's right there. It's minus 4. So it's minus 5x. That's the only way this is going to work. If I don't. So that's a minus 5x. We'd be struggling to get an answer here. Now, so I just changed those to x minus 4s. All I did. I miscopied the problem. Put pluses there. And that makes it x squared minus 4x. And then when I subtract x, I get negative 5x. And subtract 6, I get negative 6. Now that'll factor. That's x minus 6, x plus 1. X minus 6 equals 0, x plus 1 equals 0, x equals 6, or x equals negative 1. If I go back to the original problem, which one gets thrown out? Or does any of them? Negative 1. Negative 1, because the original problem had natural log of x. That negative 1 is going to mess that up right away. So 6 is the only solution that I keep out of that.
When we're doing this, we can't have negative solutions, right?
You can. You can have negative solutions. You've got to check them all. When you get a solution, check it in the original problem to make sure you're not taking the log of a negative. That's where you can't have a negative. It's inside of the log.
So when you check it in the original problem, you have to get a positive number, right?
Inside of the log, yes.
Okay.
Yes, that's correct. All right. Log base 2 to the x equals, excuse me, back up. Let's do this one. 8 times 3 to the x equals 5. Let's do that one. And we'll come back to the next. Change it up a bit. So every one we've had before had logs in it. This one doesn't have any logs in it. We're going to have to put some in there to solve it. Yeah. Because we have 3 to the x power. The exponent is on the 3, right? The variable is only 3 as an exponent. So we need to get that part by itself. How do I get the 3 to the x by itself?
Divide by 8.
Yeah, just divide by 8 first. 3 to the x equals 5 over 8. So it's equal to a fraction. That's okay. Not a big deal. So now, can you turn 5/8 into 3 to a power? If this were a 9 over here, we could turn it into 3 squared, right? If it was 27, it's 3 to the 3rd power. That sort of idea. So doing this as an exponential is not going to happen. So we're going to have to use logarithms to work this out. What log do we want to use?
Log 3.
We could use log base 3. That would work wonderfully. If I take the log base 3 of each side, what happens on the left side?
Log base 3 cancels out 3.
Yeah. Leaves us x. And that leaves us log base 3 of 5/8, which is a number. So we can get the approximation for that. We want log of 5/8 divided by log of 3. Negative 0.42. That's right. Yeah, negative 0.4278. Go 4 decimal places again. So there's the exact solution and a decimal approximation. Think about it. If you're going to raise 3 to a power and get 5/8, it better be a small number. And it's making it a small fraction to a negative small number. How that works well. Yes, ma'am.
I really hate to ask you to go back to the one before this, but I kind of don't get the whole negative numbers. Like, are you just going back and plugging it in at the end?
Yes, I'm going back to the original problem and I'm putting in natural log of -1 plus natural log of -1 minus 4. And if that stays, like when you work out anything that's happening inside of those parentheses, if that stays a negative, that's why you throw it out. That's good. I'm glad you cleared it up because that'll definitely come up as you're working through some stuff. Yeah, absolutely. All right, let's look at this one. Let's look at 2 to the x is equal to 5. Something that looks fairly simple. It is, but not anything you're going to have to do at the grocery store, but I think that would be a great way to increase math scores in the world. If you had to figure out your own prices.
Or decrease obesity.
I don't know.
I'm still mad that our the sales tax is like 0.6, 0.9 or something like that.
Yeah.
So that's why we have that.
It was it's so that it doesn't come out to be a nice even cents and they get to pocket the extra change. That's the reason. All right, so 2 to the x is equal to 5. Not the same base. We can't turn a 5 into 2 squared or something like that, something easy. So what log do we use to get rid of the 2?
Log 2.
Log base 2. There it cancels out. Got x. Hey, there's nothing else to do. It's just log base 2 of 5, which is, go 4 decimal places. Hey, how about I just do it? Log of 5. 2.3220. Now, let's look at one that's a little different. Oh no. Just when I catch on, it changes it. Jerk. I swear. All right. Now, what's different about this one?
There's complicated exponents.
Okay, complicated exponents, but that's not the biggest difference.
Oh, good.
Different bases. Oh man, we got a base 5 on one side and base 3 on the other. So using a base 5 would get rid of the 5, but it wouldn't get rid of the 3. And using a base 3 would get rid of the 3, it wouldn't get rid of the 5. Trying to come up with some other log base that would do that is futile. It's not going to help you. Okay. What we want to do is use a common log here that will get the exponents out of there. We'll have some logs still in our answer, but remember, log base whatever of 5 is a number, and log base whatever of 3 is just a number. It's a decimal number, but it's a number. Okay. So what we can do to get those exponents out of the exponent is use a natural log. That's the most common log that most textbooks use. We're going to use natural log here. When the bases are not the same and you've got an exponent in each side, you want to use a natural log to get rid of it. So we're going to take the natural log of 5 to the x minus 2 and the natural log of 3 to the 3x plus 2. What that's going to allow to happen is x minus 2 to come to the front and 3x plus 2 to come to the front. This one is pretty complicated. All we've got to remember, though, is natural log of 5 is what kind of thing? It's a what? It's a number, right? It's like the number 6. It's not 6. It's like the number 6. It's just a number, okay? What property is this now? If this is a number, what can I do to these things? Distribute. If I distribute that, that's going to get me natural log of 5 times x. Or x natural log of 5. So I'm going to distribute. So x natural log of 5 minus 2 natural log of 5. I'm going to do the same thing on the other side with the natural log of 3. So that's 3x natural log of 3 plus 2 natural log of 3. Now, the reason I'm doing that is because what am I trying to solve for? X. So I need everything that's got an x to be where? On one side of the equation. Okay? When they're locked in those parentheses, I can't do that. Okay? So I've got to get rid of some stuff. Okay? So I want to distribute so that I get this one piece has an x. Well, this piece doesn't have an x. So what can I do with it? Add it back to the other side. And then I look over here and this piece has an x. How can I get it over there with that piece? Subtract it. Yeah. I get excited about this stuff because it's fun. It's not boring high school math. Okay? So if I do that, I get x natural log of 5 equals 3x natural log of 3 plus 2 natural log of 3 plus 2 natural log of 5. Then I'm going to do what y'all said. You said subtract this guy to the other side so that all the x's are on the same side. So minus 3x natural log of 3. Minus 3x natural log of 3. That cancels out there. Okay. So we have x natural log of 5 minus 3x natural log of 3 equals 2 natural log of 3 plus 2 natural log of 5. It's long, but all you've got to remember is this is just a number. We're writing it in exact notation instead of the decimal. So this is just a number. Now, what do these two have in common? X. So what can I do with that? Factor. Then we're going to divide. Factoring and dividing are very, very similar things. The right idea. Get the x out of there by factoring it so that it's natural log of 5 minus 3 natural log of 3. The other side hadn't changed any. Just copy it down. Now, what's going on between x and this big junk in parentheses here? Now, opposite of that would be division. What am I going to divide by? What am I trying to get by itself?
So you divide by what x multiplied.
Right. I'm going to divide by this ugly stuff here. And that's a number. It's x equals 2 natural log of 3 plus 2 natural log of 5 divided by natural log of 5 minus 3 natural log of 3. And we can get a decimal approximation for such a thing as that. Thank you to the people that invented the graphing calculator. 3 natural log of 3. Not 3, actually. Back up. Start over. 2 natural log of 3. Close parentheses. Plus 2 natural log of 5. Close parentheses. That's the numerator. Divided by, then parentheses, natural log of 5 minus 3 natural log of 2. That was the denominator. Negative 11.52 35. So what y'all got? Make sure I type that all in right. 2 natural log of 3 plus 2 natural log of 5 divided by natural log of 5 minus 3 natural log of 2. Close parentheses. Yes. Negative 11.5235. No? Did I type something in wrong? Ah, it is a natural log of 3. Thank you. Okay. Back up. That divided by I'm glad you caught that because we'd have had the wrong answer in our notes. Divided by, and then natural log of 5 minus 3 natural log of 3. That's where we made the mistake. I put a natural log of 2 in there instead of natural log of 3. And hit it. Negative 3.2116 for 4 decimal places. Thank you for catching our terribly crappy error. Oh yeah, that's a lot. That's a lot going on. Is it always going to be that complicated? No. It's not always going to be that complicated. This may be the toughest ones that you get in this particular section. But it's if you can do that particular problem, you could do 100% of the others. Because that is really the most complicated that they're going to get for you to solve in this particular set of problems. Okay. All right. You good? Nope. All right. All right. Let's move on to something that's a little more applicable to everyday life, hopefully. Financial models. Compounded interest.
I wish we
Y'all had a bad experience?
Yes.
Personal finance. I think we should go back to keeping our
Personal
funds.
Not like an A.
I made damn personal finance. Just didn't like it.
Didn't like it. Well, that's the reason the state decided that everybody needed to take it.
I got an award in personal finance.
I mean, same.
No one has to do it.
All right. Compounded interest. Compound interest, what we're going to be dealing with is kind of like regular savings account interest. Okay, that when you're dealing with you invest a certain amount into an account and you leave it there, you don't touch it, and you don't put any other money in there. Okay, we'll keep it as simple as we possibly can. As you put deposits into a savings account, it really changes how long the formula lasts, and the number of times it's compounded doesn't change, but the how much time it's in there at that certain balance changes. Okay, so with this formula, here is what everything means. A is your account worth. That's how much money the account is worth after the interest has been applied. Okay, it's your account worth. The P is your principal investment. That's how much you deposit into the savings account. Okay, it's $20,000. Whoever does that into the savings account. You just got 20,000 laying around. I just gonna put it back. I don't need it. And, you know, that sort of thing. You put it in there. That's your principal investment. That's how much you put into the savings account. 1, that's the number 1. It doesn't change. It's always a 1. Okay. The R, that's your rate, your interest rate. N is the number of times compounded. That 1 is just, it's always there. It's what keeps the principal balance in there to begin with. Like, so if you're going to get 3% interest, you need 1 times whatever your principal balance was plus 3% out of that. So that 1's there to keep your original balance up to date. Okay. Now, the N is the number of times it's going to compound. So if you're compounding interest monthly, N is going to be 12 because it's number of times a year. Finance models are based on years. Okay. The T is the number of years. That N is the same N there. Okay. This is time, and it's always in years. So if they said for 6 months, you're going to say 0.5 years. Okay. So N is the number of times. If they say quarterly, how many times is that a year? 4 times a year. If they say semi-annually, 2 times a year. Okay. So daily. 300. All right, we got it. Okay, so N is going to change according to the word problem that they give you. Okay, they're going to tell you how many times the interest is going to compound. Okay, so as that number changes, it can change how much interest you gain. Usually, unless it's a large amount of money, it's not by much that it changes it, but it does change it some. Well, it's slowly, but it's still exponential, and you know, depending on the interest rates. Right now, everyday interest rates are not very good. Like I think I've got like 0.1% on a regular savings account. That's pretty common. You can invest in some mutual funds that say, okay, you give us your money and it stays here for 7 years, and we'll give you a higher interest rate. That's and you pay a penalty to get it out.
Is that like a CD?
A CD is another example of that. Yeah. A CD is a cash deposit, and they have ones at 6 months, a year, 3 years, 7 years, different amounts, get different interest rates.
Do I get a college personal finance credit for this?
No. All right, so let's do a problem. If you invest, let's take a modest amount of money, $1,500. At 2.5% interest. Quarterly for 4 years. How much is the account? And I always take this as an example for my seniors in high school. When I'm teaching them, I say, okay, so you're going to get some cash for graduation, right? That's kind of the custom around here. You send out all these invitations to people you haven't seen in years, your mom's uncle's cousin, and you send them an invitation hoping that they don't come to your graduation, but that they send a check. That's what a lot of people do. I'm not saying that's the best thing in the world to do, but it's what a lot of folks do. And sometimes that rich uncle will send you a check. And let's say you totaled all that up and you have $1,500. And because you're a smart, responsible human being, instead of blowing that at Panama City on renting scooters and other things, you decide, I'm going to put that money in the bank, and in 4 years, I'm going to graduate college. I need some money to start my life with, right? You got college, you have bills that are going to come due. You're going to need an apartment. You don't go back and live with mom and dad, okay? I'm not going to want you to come back and live with them either. So we need some money. So at 2.5% interest, we put that money in there. We're going to leave it there. We're going to see how much we got left at that end. So our formula, account worth, our principal investment is $1,500. 1 plus our interest rate is 2.5%, so that's 0.0 0.025. Quarterly, N is 4 years, 4 times a year. N times T is 4 times 4. 4 times every year for 4 years. We're just plugging all this stuff in, cranking out the account worth. We're not having to solve for anything at this point. So I'm just going to put 1,500 parentheses 1 plus 0.025 divided by 4 raised to 4 times 4 is 16. I'll just type in 16. My account is now worth $1,657.24. We got $127 and almost a quarter. $57, sorry. Chipped us about, I was taking $30 just for a finder's fee. We got $157 for doing nothing, which is a plus, right? We've gained some money by just leaving it there. That's not that we're not depositing any other money in there. We're not taking our Christmas money and putting it in there or anything. We just took that $1,500 day one, 4 years later, cash it out. This is how much our account is worth. Okay. Now, let's say we get to the more complicated part of life, and we're trying to plan for the future. Okay. How long should we leave our $1,500 in an account drawing? Let's say it's not as good, and we could only find an account that's worth 1.5% interest quarterly. To have 2,500. How long are we gonna leave it there to have $2,500 to gain $1,000? What we're trying to do, we're trying to gain $1,000 because we think, okay, I know when I get out, I'm gonna need $1,000 to furnish my apartment. I'm gonna need $1,500 because I got to put first and last month's rent. When I do that, rent's like $500. That's another $1,000. So I got $500 left to hopefully get a mini fridge or something to keep my food in, or maybe get some groceries or a suit to go to job interviews with or something. Okay, so I got $500 left. So I know I need $2,500 when I get out. So how long do I have to leave it there to have $2,500 left? Let's go find out. What's our account worth? $2,500. The principal investment was $1,500. The one always there. Our interest rate 0.15 for 1.5%. Quarterly 4 times again. We don't know what the time. T is what we're solving for. Where is T at? It's in an exponent. Thus, why this is even in the whole chapter with exponential problems, right? We've got to find out how long that's got to be there. So how do we solve this problem?
First you want to solve it, right?
No. Well, you could. I'm not going to. Just because I can type that into the calculator just as easy as I could a big long decimal. So I'd have to type out less digits, I think, by leaving it like that. How do I get the part that has the exponent by itself first? Is it?
Can you put it in front of it?
Well, no. Not yet. Yeah, absolutely. Divide by the 1,500. Let's get rid of that. That's nice because the zeros cancel. 25 divided by 15 would be 5/3. We have 1 plus 0.15 divided by 4, 4t. And now maybe I can look at getting that exponent out in front. 2,500 divided by 15.
I'm talking about the 0.15
or point.
That's 1.5% as a decimal.
Oh, okay, I see it.
What can I do to get the exponent out of the exponent? Because I got a variable in that exponent, so I can't do a root. Get rid of it. It's a big t root. Nobody does that. Well, you don't know what t is, so you don't know how to even evaluate that.
So can we put it in front of the problem? Yet?
How?
Change it to
Change it to a log. What log do I want to use here? Why? That's right, but why? Because the bases are what?
different.
Very different, right? We got 5/3 on one side, and we got this 1 plus 0.015 over 4 on the other side. So we use a natural log. It's a common log. It's used a lot. Yeah, it's like it's kind of like what it is. Okay, so the 4t comes to the front, and we got natural log of 1 plus 0.015 over 4. Now, I want to get t by itself. What's going on with t and all that other stuff? What's the 4 doing to the t? Okay, what's the 4t doing to the natural log?
So can we just divide,
Now,
can we divide by everything except t?
Everything except for t. That's exactly right. So I'm going to divide by 4, natural log, 1 plus 1 or 0.015 over 4 on both sides. So I have t is the only thing left, which is what I'm trying to solve for. So t is this interesting looking number over here. Let's work that out. Natural log of 5 divided by 3 divided by 4 times the natural log of 1 plus 0.015 divided by 4. $34, and we'll just go 2 decimal places here, 0.12 years. That's a long time. Yeah. Been away a while. Well, mom's basement for a long time. Until I retired. 34 years after graduating from high school.
Pretty cool if you're calculating it.
Yeah, sure. Yeah. So hopefully you've secured some other means of income, and you cash that out or put a lot more money in there with it. That's the idea. Okay, so I wouldn't say so. Are you putting parentheses after the 5/3? Close that. When you hit divide, did you hit a parenthesis to open up? There, parentheses 4 times natural log 1.015 divided by 4. Or 1 plus 0.015 divided by 4. Double parentheses at the end. Okay, good. Usually it's just a 1 parenthesis missing somewhere and it makes it mess up. Okay. All right. So there's compound interest. That sort of idea is what's going on there. As compound interest goes from quarterly to monthly to weekly to daily to maybe hourly, as you start increasing the number of times the interest is compounded, you get closer and closer to what's called continuous interest, which is the last thing in this section. Continuous interest is an easier formula to remember. It's the PERT formula. P times e to the RT. Okay. Much easier formula to remember. Continuous interest, the problem will say continuous interest or interest compounded continuously. It will say that word. If it's the other formula, it's going to say compounded quarterly, monthly, daily.
What exactly is compounding?
Compounding is how many times the interest is added back into the balance of the account. If it's quarterly, like every 3 months, like March the 30th was the end of the quarter for fiscal quarter for my savings account. So they put like 16 cents into my savings account from the interest rate. Okay, and then now that's the new balance, and it will carry on to the end of the next quarter, and then they will put another, maybe 17 cents. That's not good.
Not even making $1.
Man, this is
In a
smart
year.
investment.
Yeah.
Making us the tax bill by $1.
Well, you have to. You don't make enough in interest. I don't because I'm not rich. I'm a teacher. So my interest isn't even enough to claim as income.
If you have $1 though, you could like. live off
Yeah.
interest.
Yes, that's the rich folks do that. So or trust fund. That's a kind of the idea of that. All right. So let's look at one of those problems. We invest $3,000 this time at 2.75% interest, compounded continuously. For 6 years. What's it worth now? Okay. So we have this formula. It said continuously, so we know to use this formula. We want to know the account worth when $3,000 is 0.0275 times 6. Basically, we're typing this in the calculator and cranking it out and seeing how much money we got after 6 years. 3,000. E, to get E on the calculator, you're going to hit second natural log, 0.0275 times 6, the exponent in there. So we gain $538.18. 35, 38, 18 cents. That's pretty good for doing nothing.
What do? You have to like go around all the banks and find out who's got better interest.
Yeah, you can. Yeah, absolutely. And most of the local banks around here usually don't have the best rates. A national bank like Ameribank or Regions is not national. It's just Southeast. They would probably have a better interest rate than a like CB&S Bank here in town. That's who I bank with. Friends that work there is really the only reason. But the interest rates are about the same at most of the local banks. You can get higher interest rates at larger banks. But like I said, a CD, where you lock your money in for a certain amount of time, that's where you can get higher interest rates. And if you can say, hey, I got this money, I'm going to put it in there, and I'm going to forget about it for X number of time, then you get a higher interest rate. But yeah, you shop banks, really.
Well, this is ironic because this is what we're going through right now.
Yeah, it's a handy thing to know. Because you're not going to find continuous interest very much, especially at a brick and mortar bank. Online banks are probably going to have higher interest rates than a lot of the locals. Yeah, no, the credit unions are about with the banks. They're a little bit better sometimes, but not really good. One of the best ones that I've found is Farm Bureau Insurance. There's a life insurance policy that allows you to overpay your premium, and it becomes a savings account, and you have access to it, and it draws a higher interest rate than any of the banks do around here.
You just answered one of my questions because I'm thinking about switching because of all of that.
Yeah, and there's a lot of options, and it's just, are you willing to go down all those roads to find the right one for you? And some of them have good things to them, some of them don't. Let's look at one last thing in this section, and that's what if you want to double an investment?
I'll leave it with this and
How long would it take you to double an investment at 2.75% continuous interest? Okay, if you're going to double an investment, does it matter how much your investment is? It should, mathematically, it takes me the exact same amount of time to double $1 as it does to double $1,000. The time does not change. Doubling the investment doesn't matter how much your original investment was. If I'm doubling it, it's going to take me the same amount of time with an interest in a savings account type situation. So if we're going to double the interest at continuous, we know that it's this formula because it said continuous interest. If we're going to double that, what's the easiest principal investment to use? $1, right? Can't use $0 because if we double $0, it's still zero, right? Sorry about my. So $0. This is what I meant. All right. So if I'm going to double $1, I'm going to get $2 back, right? I know my interest rate is 2.75%. I want to know what time that's going to happen. Technically, what I do with this 1? Divide it. 2 divided by 1 is 2. So that 1 just goes away. How do I get my answer here? How do I get the t out of the exponent?
Log.
Which log?
Natural.
Why?
Because
Yeah, it cancels out the e, right? Natural log. So that's natural log of 2 equals 0.0275 t. Because the natural log cancels out the e. How do I get t by itself now? What is that? 25.21ish. Natural log of 2 divided by 0.0275. 25.21 years. At that interest rate. For the double in investment. So that means if I had $10,000 and I threw it in the bank and could forget about it, I'd have $20,000 in 25.21 years. If I had $1 million and I put it in at that interest rate, I'd have $2 million at the end of 25 years. Okay. So building up some interest rate stuff there. Okay. All right.